Look around. The electric revolution is here. But have you ever stopped to consider what truly powers this transition? It's not just electricity. It's a dense, complex powerhouse hidden beneath the floor of every Tesla, Ford F-15, Lightning, and Rivian. Right now, in massive, highly secretive buildings known as gigafactories, billions of individual cells are being born. This isn't just an assembly line. It's a chemical dance orchestrated by hyper-precise robotics where the slightest impurity can ruin a multi-thousand-dollar product. These factories are engineering marvels, sealed environments where temperature, humidity, and even airborne particles are meticulously controlled. What happens inside these futuristic walls? How does a handful of specialized minerals transform into the single most expensive and crucial component of your next eat? This is the journey we're taking today. Welcome to Industrial Arcana, where we pull back the curtain on the world's most impressive industrial processes. For too long, the manufacturing of EV batteries has been shrouded in misty proprietary technology locked behind secure doors. We're going deep inside the Gigafactory to reveal the entire mind-bending process. We'll start with the foundational materials, the raw earth minerals, and follow them, step by step, through the highly technical stages of mixing, coating, cell stacking, and electrolyte filling. By the end of this video, you will not only understand how these batteries are made, but you'll appreciate the sheer scale of the precision engineering required. This process is necessary to deliver the safety, range, and performance that is rapidly redefining modern transportation. The genesis of an electric car battery begins not on the factory floor, but deep underground. The critical components are a few specialized minerals: lithium, cobalt, nickel, manganese, and graphite. Lithium, often mined from brine pools or hard rock, serves as the critical ion carrier, moving back and forth between the electrodes to generate current. Nickel is prized for its ability to increase energy density, allowing the battery to store more energy, and thus increasing the vehicle's range. This is why modern high-performance EVs rely heavily on high-nickel cathodes. Cobalt plays a crucial role in stabilizing the cathode structure, preventing it from degrading too quickly during charging and discharging cycles. Graphite, meanwhile, forms the anode structure. These raw materials arrive at the Gigafactory in highly purified forms, often as powders, ready for the first, crucial stage of preparation. This reliance on global sourcing highlights why the EV transition is also an intense geopolitical and resource challenge that dominates supply chain discussions across the industry. Before anything can be coated, the active materials must be transformed into a precisely formulated slurry, akin to a high-tech paint. This slurry is the heart of the cell chemistry. Imagine giant, sealed mixers, where the powdered cathode material like lithium, nickel, and cobalt is combined with conductive additives, typically carbon black, and a solvent. This mixture must be perfectly homogeneous. Any clumps or uneven distribution will result in poor performance, hotspots, and a shortened battery life. The solvent is necessary to ensure the slurry can be evenly spread onto the metal foil later on. Its specific formulation is a tightly guarded secret, influencing everything from performance to cost. The same rigorous mixing process is applied to the anode materials, primarily graphite. This mixing stage is performed in pristine, dry rooms because moisture is the battery cell's worst enemy, reacting with lithium compounds and degrading the cell instantly. The quality and consistency of this slurry determine the battery's fundamental characteristics: its power, its lifespan, and its safety under stress. With the slurry mixed to perfection, the next step is perhaps the most visually impressive: the coating process. The slurry is pumped through precision dispensing heads onto large rolls of ultra-thin metal foil. Aluminum foil is used for the cathode positive and copper foil for the anode negative. The foil is run at high speed through a coating machine that applies the slurry layer with micron-level accuracy, ensuring uniform thickness across the entire width. This precision is non-negotiable, as variations in coating thickness lead to uneven current flow and premature cell failure. After coating, the foil must be dried to evaporate the solvent completely. This drying process happens in enormous ovens that maintain meticulous temperature control. The residual solvent is captured and recycled, minimizing environmental impact and material waste, a critical factor in gigafactory economics. Finally, the dried, coated foil is compacted through high-pressure rollers, a step called calendering, which compresses the material to the exact density required. The continuous roll of coated and calendared material is now ready to be transformed from a flat sheet into individual, functional electrodes. This begins with slitting, where the wide rolls are cut into narrow, precise strips corresponding to the cell's final dimensions. These strips are then moved to automated machinery for the actual cell assembly. In cylindrical cells, the strips are carefully wound together, while in prismatic and pouch cells, they are stacked. Stacking is a high-speed, highly repetitive ballet, performed entirely by robots in the clean room. The machine meticulously layers the cathode, separator, and anode in a repeating pattern. The separator, a critical plastic film thinner than human hair, must never touch the positive and negative electrodes. If it does, it causes an internal short circuit, leading to thermal runaway and cell failure. The speed, accuracy, and sheer volume of cells produced daily in this stacking process highlight the enormous capital investment required for mass EV battery production. Once the electrodes are stacked or wound and placed into their final housing, the cell is ready for electrolyte filling. The electrolyte is the medium that allows the lithium ions to shuttle back and forth between the anode and cathode. It is a highly flammable, specialized blend of organic solvents and lithium salts. Filling the electrolyte must be done under a deep vacuum to remove all air and moisture from inside the cell, ensuring a perfect, non-reactive environment. This process is complex because the filling must be slow and steady to allow the viscous liquid to fully penetrate all the porous electrode materials without forming air pockets. After filling, the cells are immediately and hermetically sealed. For pouch cells, this involves heat sealing the edges. For cylindrical cells, a complex crimping and laser welding process secures the cap. The seal must be absolutely perfect, as any leakage would not only pose a safety hazard but also allow moisture ingress, leading to cell degradation and rapid failure. The sealed cell is chemically complete, but it is not yet a functioning battery. It needs to be formed through a precise, controlled charging and discharging cycle. This first charge is arguably the most critical step in determining the cell's longevity and stability. During formation, a solid electrolyte interface, or say layer, is deliberately created on the surface of the anode. The say layer is a passivation film that is essential for long-term cell stability, allowing ions to pass through while preventing further reactions between the electrolyte and the anode. This process is time-consuming. It can take several hours or even days and generates heat. The cells are placed in temperature-controlled rooms, often called aging rooms. Any defects in the cell's construction or material consistency will manifest during formation through abnormal voltage or temperature spikes. Cells that fail this crucial initial test are sorted out and sent for recycling, ensuring that only perfectly healthy cells continue to the next stages. After aging, thousands of individual cells are gathered and transformed into a powerful battery pack, ready for the vehicle. First, cells are assembled into larger units called modules. A module typically holds dozens of cells wired together with boosts, which are thick, metallic strips that conduct high current. The modules are also integrated with thermal management hardware, often including cooling plates that snake between the cells to regulate temperature. Maintaining an optimal temperature, usually around $25, circ-tex, $, is crucial for maximizing battery life and performance. Multiple modules are then enclosed together inside a rugged, impact-resistant casing to form the final battery pack. The pack is integrated with sophisticated electronics. The battery management system, the BMS, is the brain of the pack, constantly monitoring the voltage, current, and temperature of every single cell. This system ensures safe operation and optimizing performance across the entire system. Before a finished battery pack is shipped to the automotive assembly plant, it must endure a gauntlet of rigorous quality control and testing procedures. Each pack undergoes extensive electrical testing to confirm the total capacity and power output meet the specified requirements. The BMS is thoroughly checked to ensure all sensors and safety protocols are fully operational. Perhaps the most dramatic tests involve simulating extreme conditions, vibration testing to mimic years of bumpy road use, and thermal cycling to check performance in intense, hot and cold weather. Crucial safety assessments like crush tests and penetration tests are done to ensure the physical integrity of the enclosure and the prevention of thermal runaway in an accident. Only a pack that passes every single metric is deemed roadworthy. The astonishing precision of manufacturing, combined with these exhaustive quality checks, is what gives EV batteries their reputation for high reliability, enabling the electric revolution. The engineering that goes into these batteries is phenomenal, transforming raw earth into a powerful, precise energy source. But this is just one piece of the puzzle of industrial might. If you were fascinated by the secrets we revealed inside the Gigafactory, make sure you hit that subscribe button. We're dedicated to bringing you the hidden workings of the world's most advanced machinery and production lines. Don't miss our next deep dive into cutting-edge technologies. Subscribe now to Industrial Arcana.